So, just so you are aware, anybody want to shout out what their first car was?
My dad, Prius.
Yeah.
Okay.
Right? So, Mrs. Hill's first car, this is not Mrs. Hill, but it looks like it. Mrs. Hill's first car was a Pinto. Mr. Ross was, I'm not quite sure what that one was. My first car was a white Jetta, 2-door, white Jetta. And then Mr. H's first car looks like a Malibu? Or it looks like a Malibu. Impalas are bigger. Yeah. Okay? Right? Pintos had the gas tank in the rear. It was like right in front of the rear bumper. So when they got hit from behind, they blew up.
My dad had a car like that.
Yeah.
Beetles.
Oh.
Yep.
Bugs.
Bugs? No, Bugs had the engine was in the rear.
Yeah. So it
Yeah.
blew up even more.
Yeah. Yeah.
Oh,
All right.
perfect.
So here we go. Are we on a leaf problem? Suppose you rake. Yes, we are. Suppose you rake your yard. And before you get the rake hung up in the garage, it's that time of year again, there are 50 leaves on the
Yeah, that's something for tomorrow.
Exactly. And the number of leaves continues to increase by 8% every hour, which means there's more leaves fall. Find the number of leaves on the ground 12 hours after you finish raking. All right? Well, let's get an exponential model. Okay? Remember from the other day, an exponential equation is going to be of the y equals a times b to the x power. That's what we're going to want to create here. Y equals a times b to the x power. Okay? So let's create one of those. So after 0 hours, so we don't even get the rake hung up in the garage, 50 leaves. Okay? 1 hour later, how many, and you all have a calculator in order to calculate this, how many leaves are on the ground? $54? Do we agree with 54? Yep. I would agree that there are 54 leaves on the ground after 1 hour. How many are on the ground 2 hours later? 58.32. Okay. How did you come up with that?
Took 54 times 0.08. And then I
added it to it? Okay. Anybody come up with it a different way? That worked. That worked. No, we cannot do it by 16%. Nope. 16% would put us at 58 even. So what's another way of doing this? So let's go back to 54, because then our numbers are nice and easy. So one method is we took 50 times 0.08 and then added that to 50 to get 54. Agreed? Why is is that not this? Agree?
Yeah.
Okay, what's another way of doing it?
The 50 times 0.08 power. Whatever.
No.
Power.
Nope. Even easier. What do you got? 1.08 is the other way of doing it. Why do you multiply by 1.08? Anybody know? And then you can take 54 times 1.08. And then you can take 58.32 times 1.08. And then you can take whatever you get there times 1.08. Okay? You know why that's the easier way? Well, let me break down this math right here. If I factor a 50 out, right, what's left over? .08 plus what? Nope. If I factor a 50 out, 1. What's .08 plus 1? 1.08. Okay. Single step shopping as opposed to multiple step shopping. Multiple steps still gets us there. I can go to Mosinee by going through Marathon and coming back in the back way. Okay? Or I can just do single step, just jump on the highway and go to Mosinee. Okay? Gets me to the same spot. Okay? Alright? So now let's come up with a function based off of 3 data points that gives us, for any time x. So let's go y equals, or let's go our leaf function. A, what's our A value going to be? 50. Starting value. A is our starting value. So A is 50. B. What are we multiplying by every single time? 1.08. To the x out. Okay? How many leaves are on the ground in 12 hours? Agree? Leaves on the ground. So if a population, or in a population P, is changing at a constant percentage rate each year, then P of T equals P sub 0 times the quantity 1 plus or minus R to the T power, where P sub 0 is the initial population, T is the time in years, the key is that is in years, and R is your rate as a decimal. Now, if your population is growing, you would add R. If your population is decreasing, you would subtract R. You need a decay, so that value has to be below 1. Okay? So that's why it's plus or minus R in there to add in for growth or decay. And that's a population of anything. That could be a population of leaves, like we just did, okay, where it's changing at 8% every hour. Okay. That could be a population of some kind of an organism, something along that line. Could be a population of a city. Okay. Example number 2. Determine the exponential function with an initial value of 12 and increasing at a rate of 3.5% per year. Okay? So again, we want to go y equals a times b to the x. Or, if we really wanted to go right above it, we could go p of t equals p sub 0 times 1 plus or minus r to the t power. Both of those are going to give us the exact same answer. What is our function? Initial value? 12. We growing or are we decaying? Growing, so that's plus. So what is my growth rate?
1.
Too many. So what do you got? Just 1.035. You said 1 plus 1.035. So you were actually 1 too many. Raised to the x power, because I defined x as my variable. Okay? Second favorite example of the year. Right here. Example number 3. You purchased yourself a 1979 Ford Pinto back in 1985. That was valued then at $1,800. Classic Pinto. White with a red racing stripe. Starsky and Hutch style. Sport rims. If you went to Greenway High School in Duluth, Minnesota, you were the talk of the town. Okay? Hard to believe, but somehow this hot rod actually lost value at a rate of 7% each year. Find an exponential function that describes the value of this classic as a function of t in years since 1985, and then find the value of said Pinto in 1990. Okay? And for those of you that don't know, this one is one of us. To add to the legend, it didn't make it to 1990 because she got total delivering pizzas for Domino's in 1989. So, first off, we had to find the function. Okay? So the function is going to be, we'll say, value of t. So I'm going to label my function v of t. Okay? So the initial value was 1,800. It goes down by 7%. That means it's going to be 0.93 t, or to the t power. Okay? If I plug in, then 1990 is how many years since 1985? 5. So I'm going to plug in 5. I'm going to find V of 5. If V is 5, then the value in 1990 should be $1,252.24. What would the value be today? So in 2021? Probably not, right? Well, what would it be? How many years since 1985? 36, right? So 36 years out. Okay.
It's worth $132.
She's also fired.
And 2 cents? $132.02? Okay? Okay? Love it. What? That a Pinto's only worth 130?
Like the accuracy of the dates and stuff. That was what makes it longer.
Yeah.
But it's also from 1979, so we have to chop
So
off
she bought it
6 years.
used.
So we have to chop off another 6
in
years.
1985.
Mrs. Hill?
Yeah.
Yeah, we do. In 1985.
Do you think that she's not? Do you think that she's younger than that?
Yeah.
She's not. She's an old lady.
She looks younger.
She does. Okay. All right. Now we're on the back side. Okay. So suppose the population of San Jose is following an exponential growth pattern. In 1990, the population of San Jose was approximately 782,000. In 2000, it grew to approximately 895,000 people. Let's create 2 ordered pairs from the given information. Okay? So, what year, what t value should we go with for 1990? 0. I go with 0 because we always want that 0 because we want that initial value. So we always want a 0 in there. Okay? So 0 is 782,000. Okay? If that's the case, if 0 is 1990, then 2000 is year 10. Use those 2 data points to find an exponential model of the form P of t equals a times b to the t, where t is the time in years, and a represents the initial population when t is equal to 0. I like this one. How are we going to do that? Do we know A or B? That's the 2 things we got to find. A and B. What's A? Bingo. Okay. We know A. Do we know B?
No.
So we got to find B, right? Okay. So We've used the first data point. Now let's use the second data point. P of t, I'm actually going to even call it here P of t, right there, is 895,000. So we know that 895,000 is P of t. We know that A is 782,000. We don't know what B is, but do we know what T is? What is it? 10. It's 10. So we need to solve that equation for B. How am I going to solve that equation for B?
Subtract 7,782,000.
Do we agree with subtracting? Why not? It's multiplication, so we should divide instead. Okay? So I'm going to have to divide both sides by 782,000. That's going to give me that. Now what? Tenth roots both sides. Yep. Root of 895 divided by 782 is approximately more decimal points is better. If we're not going to leave it the exact. Now, can we make a model? So P of t is equal to what? 782,000 times 1.01359 to the t power, because t was our defined variable. Okay? According to our model again was you tell me what the population of San Jose was in 2005. Then, sketch the graph. Then, tell me when approximately they got to 1 million people. Then, we'll talk. So 2005 is the 15th year after 1990. 957,483.2306. Now, I used it as is, or I shouldn't say I used it the exact way. If I would have used 1.01359, seven 506.0148. It depends on which B you use. Okay? If you use the 1.01359 rounded to that, okay, then you got the bottom number. You should have gotten the bottom number. If you left it exact on your calculator, you should have gotten the top number. Okay? Okay? So there should be approximately somewhere in the neighborhood of 957,000. We'll use the rounded one. 506 people. Can I have decimal points?
No.
Why not?
Less than a whole.
Can't have less than a whole person. Okay? Alright. Sketch a graph of the model. Label your axes with words. Okay, we like labeling things with words. So that's going to be that. That's what it should look like. It's growing. Okay? So my label for horizontally, so here is year 0. Here is year 15, let's say. And that would be time after 1990. That would be an applicable label down there. Time is not enough because we started our 0 year was 1990. We have to put that somewhere in there. Vertically, I would label it as population. This would be 782,000. This would be 957,506-ish, somewhere in that range, because then when those two intersect, that's what we got. Assuming that the population was able to grow, what year did the population surpass 1 million people? 1,000 million. 2, 3, that, then how many years did we get this? Solving it graphically, we would put you should have put somewhere up in here, you should have put another line at 1 million. And then found, label it better, and then find that intersection point. Okay. Should be approximately in the be approximately, you should get something in the neighborhood of 18.2169 in there, which would be year 18 after 1990, which would really be, what? 2008. For the remaining 10 minutes, what I'd like you to do is I'd like you to create a model for Columbus, Ohio, given the following data, and then find when the data, or when your model, exceeds 800,000 people. What's up?
So how do I type in the equation? Because I tried to go back to like the previous equation of my one million people, but that wouldn't work. And so now we're trying to do this one. I'm
Okay.
trying to find what's fast.
All right, give me a second. Let me finish off my equation here. So we have 633,000 times 1.0169 to the t power. Okay. So there is my function. Boom, there it is. Can't see it. And then my second function is going to be 800,000. Boom, there it is. Now I already know that my window, I'm going to have to move out way up. Okay, so X is, okay, so to bring you up to speed, or to back up to speed here. Now bringing you back up to speed, there's my equation, typed it in, that's my blue line. My next one down, 800,000, that's what I want it to be at, that's my next line. Escape out of there. Then I found the intersection of those 2 points. That tells me that in 20 years, it will be 800,000 people in Columbus, Ohio. So, back to here, then, so the Columbus would exceed 800,000 people 20 years after that, so that means sometime in 2010.